Thank you, Bernard, for the introduction and for the invitation. I'm very happy to talk about some comparison theorems that old and new and their applications in minimal surfaces. So let me start to tell you about the one of the most classic comparison theorem. That's the theorem of Bonnet-Myers. That says that if the Ricci curvature is bounded from below by a constant, then the diameter is uniformly bounded by a constant. So for the proof of this, we compute given a distance minimizing geodesic between 2 points. We take all the orthonormal directions uh, to that geodesic, and we sum up the second variation along that. Then we get that the Ricci curvature term appears in the second variation. And if we plug in phi is equal to sine of pi over L naught t, where L naught is L0 is the length of this geodesic, then you can get that L0 has to be bounded by pi. And now if we generalize length into into higher dimension, we get minimal surfaces. And this is a theorem of Simon's. He computed the second variation of minimal surfaces. And for example, if you assume the Ricci curvature of the ambient manifold is strictly positive, and if your minimal surface is closed, this means that you can choose the compactly supported function phi to be equal to 1 everywhere on sigma. Then you will get that Ricci strictly positive will give you a contradiction to the second variation. So there is no stable two-sided minimal hypersurface. And if Ricci is greater or equal to 0, then it has to be totally geodesic by this second variation formula. And then Sheng Yao also look at the second variation, and they realize that, sorry, I think that's one more. Yeah, sorry, I'm jumping too much in front. And for free boundary minimal hypersurfaces, so when you compute the second variation, you also have a boundary term. So now you can just classify, you can look at not only the Ricci curvature, but also the second variation. So if one of them has a strict sign, then this also cannot exist. Now, Shen Yao also look at the second variation, and they use the Gauss-Kadazi equation to change, to rearrange the second variation so that it relates to the second curvature, to the scalar curvature. And we can also change the second fundamental form term to become the difference of the mean curvature of the free boundary minimal surface inside the manifold with boundary. Now, what they realized is that if you look at this term, the interior terms, you can understand this as the first variation of this operator that relates to the conformal Laplacian, and that tells you it has a positive first eigenvalue. And and if you apply a conformal change using this eigenfunction, then your manifold, when the minimal surface is closed, then you get a PSC metric. And even but this whole spectral sense of positive scalar curvature makes sense even if sigma is non-compact. Similarly, you also have this spectral sense of positive mean curvature, which can be described like this. And now, what they observed is that if you have a stable minimal hypersurface inside of an ambient manifold of PSC, then it also has PSC. And in terms of surfaces, a surface of PSC, and even in the spectral sense, PSC, in the same metric, you can compute that, and you can get a diameter bound in terms of a constant that only depends on the ambient manifold PSC. And you can also get an area bound. So that's what Shen Yao proved, that if you're a stable two-sided minimal surface in an ambient 3 manifold with uniform PSC, then you have a uniform bound in diameter and area. Now, this method of Shen Yao can be applied even inductively. So let me look at this. So you can, and Shen Yao can use this to prove that the torus, in particular, the torus connect sum with a closed manifold has no metric of PSE, and we can give a heuristic of the proof by looking at the picture where we can look at the torus and we can, for example, minimize. We take the torus as the first slice, so that's the sigma 0. And in the second slice, we want to find the minimal hypersurface inside the torus that behaves like the n-1 torus. And you will really make sense of this rigorously in terms of homology. So you minimize in the homology class, and you will get a stable minimal hypersurface. And by what Shen and Yao observed, it will have PSC, and that's your sigma 1. And now you can continue with sigma 1 to get sigma 2 that also has stable, that's also a stable minimal hypersurface inside sigma 1, and it also has PSC. And you can continue doing so until eventually you get a surface. And inductively, you will obtain that it has non-trivial H1, but also it will also has PSC. Well, the second part implies that it has to be a sphere by Gauss-Bonnet for surfaces, and that's a contradiction for it to have non-trivial H1, and that will give you the heuristic of the Shen-Yao inductive method. And this has important applications, for example, as in the positive mass theorem, where they prove that if you have non-negative scalar curvature, and if the mass is non-negative, then its mass has to, and if the dimension is between 3 and 7, where you don't have a singularity issue with respect to this minimizing process, then the ADM mass has to be non-negative. And it's equal to 0 if and only if it's isometric to a Euclidean space. So that's a very useful tool to find stable minimal hypersurfaces. But one problem is that they don't always exist, so we cannot always find stable minimal hypersurfaces in an arbitrary manifold. And Gromov generalized this to an object called mu bubble. And let me just briefly tell you what is the mu bubble. So it's a minimizer to area plus another potential term, which we define H to be defined on some open set of my ambient manifold. And now let's imagine now M is just the sphere. Then what I'm doing is that I am looking at a domain in the sphere. So for example, the lower part of the hemisphere, the lower hemisphere, then I'm looking at the boundary, the area of the boundary. So this part. That's the first term I want to minimize. Then I want to also integrate the potential along a potential that I choose in the domain omega. And I will specifically choose the potential so that I will always find a minimizer, and also it's related to my assumption on scalar curvature. So now, if you probably already realized that if H is equal to 0, then this is just the area functional, so you would just get a minimizer to area. And if n is less than or equal to 7, then a minimizer or a mu bubble is actually always smooth. So in this talk, we will also talk about only the smooth cases, so we will not worry about the singularity issue for mu bubbles. Now, if you compute the phase variation, the first term will give you the mean curvature term, and the second term will give you H restricted to sigma. So that you give that on your mu bubble, the mean curvature is the one you prescribed. It's the function H that you prescribed to be. So it's also called the prescribed mean curvature functional. Now, to get a better understanding of mu bubble, I think one of the most I guess trivial thing you can prove using it is to use this to prove the Bonnet-Myers theorem, and it gives you a good understanding of how mu bubble works. So now I have a manifold with Ricci lower bound n-1, and I want to prove that the diameter has to be bounded by pi. So I want to prove d0 is bounded by pi. And the h I prescribe is that, let's say for simplicity, that my diameter is obtained by 2 points, p plus and p minus. Then my h and their distance is equal to d0. I want to prove this is bounded by pi. Then the h I prescribed is that it's equal to tangenting of, so pi over d0, and here r is the distance to the point p minus. So when r is equal to 0 at the point p minus, you get tangent of minus pi over 2, which is negative infinity. And when you are at the point p plus, then you reach plus infinity. So the function looks like this on your manifold. And now remember, the thing we want to minimize is area of the boundary minus omega h. So naturally, you always want to contain the part where h is very large, so h is plus infinity, and where h is very and you want to be disjoint from the part where h is very small, so when h is negative infinity. So if you carefully compute the first variation, using a similar computation to the maximum principle, you realize that you will always get a minimizer that lies in between p plus and p minus, and I call this omega, and the boundary is equal to sigma. So this is now my mu bubble that I obtained. Now let's look at the second variation of this mu bubble. So if I compute the second variation, now because I want to look at Ricci, so I didn't change it to scalar curvature. Now Ricci is bounded below by n-1, we know. And now for second fundamental form, we bound it by Cauchy-Schwarz. And then we combined with the mean curvature, which by first variation, we know it's equal to h. So we get the second term here. And then the third term, we just pass it to here. And now we can always put phi is equal to 1, because this is a very good property of mu bubble, is that once you find them, they always exist, and you can always confine them to be in the bounded region band, and it's always compact. So you can just plug in phi equal to 1. Now you're just left with essentially an ODE to compute. So if you compute the equation for h, you get this is the term inside, and it's non-negative. And the constant term then has to be negative. So you get 1 minus pi over d0 is less than or equal to 0. And d0 has to be bounded by pi. So using mu bubble, you can prove, for example, Bonnet-Myers like this. Then Gromov, this is the idea of the proof of bandwidth estimate by Gromov, where he proved that if you are a band over a torus, and if you have a lower bound on scalar curvature, then the distance between the top slice and the bottom slice has to be bounded by a constant that only depend on the bound on scalar curvature. And the idea is similar to the above proof. So now we have a band of torus. Let me draw a band of torus here. And now if the distance between the top slice and the bottom slice, I call the top slice here and the bottom slice here, is going to be too large, if it's larger than this number, then we try to prescribe the same idea that h is equal to minus infinity and plus infinity here. And then we get a mu bubble inside the band, which we call sigma. And if the distance is large enough, when you compute the second variation, then again you get sigma actually has PSC. So this follows from the second variation. Now, but also because of the structure of the band, sigma also maps to the torus with non-zero degree. So sigma maps to Tn with non-zero degree. And that's a contradiction because we know the torus does not have a metric PSE, at least in this range. So you can prove this using mu bubble. So now I think this is a good time to take a break before we move on. So let me ask or check if there's any question from the audience.
I have an elementary question. So when you apply the descent method, you went down to dimension 2 and then you argued with surfaces admitting PSC metrics. Can you, in this context, also go down to dimension 1 all the way and argue that S1 doesn't have a PSC metric, or is this not possible?
Uh, so I guess in the case of the torus, uh, so yeah, I haven't thought about this very carefully.
Mm,
So I think the proof is more general, so it's not only for a torus. Like you can apply a similar proof if you maps to the torus with non-zero degree, so that or like even if you just assume that you have these one forms that gives you the non-trivial top or non-trivial h minus one of your manifold. So it doesn't have to be the case of the torus. So their proof is more general.
mm,
I think maybe for the torus you do have like easier arguments.
mm,
So in general, you just have these one forms such that uh, so you just have to make sure that on each step when you induct, you have a non-trivial homology to have a minimal hypersurface, and then that goes on to the next step. So that's the only requirement you will need.
mhm.
Yeah. Thank you for the question. And I'm not sure if that's a good answer, but
I'm always a little bit worried about some of the constants. Maybe there is some n minus 2 appearing somewhere, or I'm always a little bit confused about that. So, but yeah.
yeah, I think for the torus, maybe that you're right that you can maybe induct more, but I
Mm.
haven't thought very uh, in de detail in that. Yeah.
And also another question that comes to your mind is if you, so what kind of orientability assumptions do you really need for this type of argument? So the
Oh
normal
yeah.
bundle has to be oriented, right? But if the,
Um, so I think I am talking about, so in my context the manifolds are orientable. Yeah.
okay.
Or if that wasn't clear. Yeah.
So it seems to me that it's really enough to assume, or should be enough to assume that the normal bundle is orientable. And this
Um,
might also happen if the ambient manifold is not orientable and the um, manifold, the hypersurface, is not orientable either.
yeah. So um
Hmm.
yeah, so then I guess the minimizing you will go through a different minimizing class in the GMT process, but I think maybe that's right, yeah.
Hmm. Are there any more questions concerning the first part of the talk? Okay.
Yeah, so in my context, all the minimizing process are easier than the actual GMT. You don't really need because we're hypersurfaces, so you don't really need to use currents like all the mu bubbles. You just need them to be like sets of finite parameters or like Caccioppoli sets. So essentially, their characteristic functions are BV functions. So that will give you something that's two-sided inside the ambient manifold itself. So it you yeah, that in that sense you also don't really care if the manifold is orientable or not, I think. Yeah. So it's probably an easier process.
Thank you.
Okay, any more question before we move on? Okay, so now let's move to the uh case. Okay, yeah, I need to go a little bit more afterwards here. Okay, so Um, the same way as in the case of manifold with boundary, you can find free boundary minimal hypersurfaces, and they inherit the PSC and also the mean convex property from the ambient manifold. And we've seen that in the first slide, but they are also not always, you cannot always find stable free boundary minimal hypersurfaces. And uh, so the analogous generalization in this case will be something called the theta bubble, where you don't put the potential on the interior manifold, but you put the potential on the boundary. And so now I'm not looking at a manifold that looks like the sphere, but I'm not looking at a manifold that looks like, for example, the unit ball in Rn. So I have a function I prescribe on the boundary of the ball. And now uh, if I have an open set omega inside the ball, I can compute the area of its boundary the same way. But now the boundary of the domain itself also has a boundary. Now, we also, in the second term in the potential, we're integrating the uh, we're integrating of the domain where it intersect the boundary. So we're only integrating the part that lies on the boundary. And if you compute the first and second variation of this, you get the mean curvature is equal to 0 because the interior part is the same. But when you compute the boundary part, you will get that the angle of two vectors has to be the one you prescribed. And let me now tell you which two vector this is. Okay, let me maybe draw here. It's larger. So in the ball, I have this disk, and it has an outward pointing unit normal. And the boundary of the disk lies inside the boundary, also has a unit normal that lies inside the boundary. And the angle between these two has to be the one you prescribed when you compute, when you minimize this energy. And in fact, you can look at all the geodesic disk inside the ball. And if you compute uh, the energy for all these balls, including the point, you'll get they're all the same. So they are all minimizers to this single potential, and where theta is equal to constant. And when theta is equal to constant, you call those capillary surfaces. But but when you prescribe the angle, it's more general, and you can try to um, um, and you will get more terms in the second variation, where you can use to leverage the mean curvature of the boundary. So this is what we want to minimize. This is the energy we want to minimize. And as an example of the use of theta bubble, we will show a bandwidth estimate in the case where a band over a manifold with boundary. So for surfaces, let me look at an orientable surface uh, with a non-negative Euler characteristic, and let me look at a band over this surface. So a classic example you can imagine with this is you look at the part of a solid torus. So if I draw the solid torus, if you slice horizontally with the solid torus, you will get these annulus. So let me now draw an annulus and draw a band over the annulus. And that's part of the solid torus we have. And of course, the solid torus also close up on top and at the bottom. And it's a smooth manifold with mean curvature positive. And we talk about the band part to be of the boundary to be the partial 0M. And if I know that the overall mean curvature of this band is positive, and I know that the wall part of this band has a uniform bound on mean curvature, then I can give a bound on the distance between the top and the bottom band. So here is sigma plus, here is sigma minus. So what we are trying to prove is that, let me use another color. If these two parts are too far away at the boundary, then I can prescribe my theta or my cosine theta to be -1 here, and my cosine theta to be +1 here. And if the length is too large, then I can find a theta bubble inside that also has the same positivity condition. So I think we need to, so let me call the theta bubble here sigma. And now we need to look at the second variation of the theta bubble to make sense of the positivity condition. So this is when I was describing how the band looked like. And now the second variation of the theta bubble look like this. So if you look at the interior term, this is the same that tells you the scalar curvature is non-negative in the spectral sense. And if you look at the boundary term, now if the distance is large, then to go from plus and -1, I have a very small derivative. So now this term becomes small relatively compared to the mean curvature term. So now this term dominates, and it says that spectrally my theta bubble has strictly positive mean curvature. And now this should tell me that sigma with these conditions has to be a disk. So the sigma I obtained between these two bands has to be a disk. But now it also maps to the bottom with a non-zero degree. And we know that the bottom is a surface with non-negative second, non-positive Euler characteristic. And that's a contradiction to Nasser's theorem. So if you map it to, and we also have the map has, if you map it to a surface has non-negative Euler characteristic, you also need to have non-negative Euler characteristic. Non-positive Euler characteristic.
Where did
And
you use the assumption that the mean curvature on the left and right hand part is bounded below by 1?
the left and this part, the wall part,
Yes.
this part. Uh, so yeah, so we really want this term to be greater or equal to 0. So if this is greater than 1, and then now cosine theta has to go from
Okay.
+1 and from -1 in the distance in between pi. So this tells you theta. So yeah, this is the term I use where the mean curvature is greater than 1. So I need this to be large so that when the distance is large, this term is small, then I have this term is strictly positive. So that's really the only thing I need. And any question before we finish this, before we go on to the next topic?
Thank you. It's very clear so far.
Yeah, okay, yeah, thank you. So now another application of Urysohn width is of theta bubble has to do with Urysohn width. And let me tell you what is Urysohn width. So for a compact geometric space, we say that it has Urysohn width bounded above by D0. If you can map it to a k-dimensional simplicial complex such that the dimension of each fiber is bounded by D0. So for example, if I have just a square, then I can map it to a line so that the diameter of each fiber is bounded by 1. So if I have the square, then a unit square, I know that the U1 is bounded by 1. I know that I can map it to itself so that the preimage of each point is just a point. So U2 is equal to 0. And U0 is just the diameter. So we know that it's bounded by square root of 2. So for a compact manifold, you always have all the Urysohn widths are finite. And in fact, this is one way you can, and you have this monotonicity of the k-dimensional Urysohn widths. And in fact, you can define the topological dimension this way. So you can always map to itself so that each preimage is just a point. And you can also prove that the n-1 Urysohn width has to be always positive. So your topological dimension is just so the least or the largest the least n, so that you have a non-zero. You have a non-positive Urysohn width. And now any compact manifold has finite U0, and if you have a positive Ricci bound, you get a uniform bound on U0. That's Bonnet-Myers. And what Gromov looked at is that if you have a closed manifold and if you have uniform PSC, then you will get a uniform bound on the n-2 on U n-2. And the constant only depend on n and also the scalar curvature. And we say a metric space has microscopic dimension k if k is the least integer, so that it has finite k Urysohn width. So this conjecture is saying that if you have uniform PSC, then you look like n-2 dimensional in the macroscopic sense. So this is the definition of Urysohn width. And for the conjecture of Gromov, this is only proved in dimension 3. And so this was first confirmed in Gromov-Lawson's paper, and then recently it's further proved using mu bubble by Chodosh Lee, Lyubomirsky Maximo, and Lyubomirsky 1. And now, following the same idea, we can prove that if you have non-negative scalar curvature and uniform positive mean curvature, then the boundary looks like one-dimensional. So we can give a uniform bound on the boundary of the manifold by the uniform bound on the mean curvature. So, and so any question about the statement of the theorem? So if not, let's move on to how we can approach this problem. So if first there is this assumption of simply connectedness here. So this is also assumed in the paper of Chodosh and Lee. And even with this assumption, you can actually use this result to prove many useful results we will mention later. But if your manifold is closed, this go back to an idea of Gromov, then you can maybe remove the assumption of simply connectedness by first try to slice your manifolds using its homology. But if your manifold is complete, it's not clear if this assumption can be removed. Maybe you will need to assume that your manifold has finitely generated fundamental group or something like that. So now let's look at the case where the manifold is simply connected and see how we can try to prove this theorem using Theta-bubble. So now our manifold is simply connected, so it may have many ends, but the ends cannot be too intertwined, so they cannot be connected to each other in a weird sense. So now I can look at a base point P and look at the band at P of fixed length. So let me call this band. This is the band that's at distance k pi from P, and this is the band at distance k plus 1 pi from P, and this is the band at distance k plus 2 pi from P. Now, we know that if the manifold, so from the previous example, we've seen that if the band is long enough, so in this case, it's pi here, and I have PSC, then I can construct a theta bubble inside. So in this case, it's just in here, so that it has so that the theta bubble also has PSC. So this is, and now having a uniform bound and being a theta bubble inside the manifold with PSC, this gives us that, so let me call this sigma K and the sigma K plus, that the sigma K and sigma K plus has a uniform diameter bound. So in fact, if you look at their length, their intrinsic length, so this is the length that lies inside the boundary, it's bounded, and also the distance of every point to the distance of every point to the boundary intrinsically is also bounded. So we're not looking at the distance of this disk lying inside of the ambient manifold. We're actually looking at the intrinsic distance, which you can show. So all these has bounded diameter. So now I can look at the manifold that's being chopped up by my theta bubble. Sorry, like this. And I can show that now this part has bounded diameter. And the way we do it is to connect every point in this part to its end, the end it's coming from. And because my manifold is simply connected, we know that it has to connect, it has to go back to the same end. Now they must intersect the theta bubble, the same theta bubble at some points. And now we know that these two distance has a uniform bound, and these two distance also has a uniform bound. So now you can say that the whole chunk that's chopped up by the theta bubble also has a uniform bound. So that's how you bound the Urysohn widths of the boundary of the manifold. And one immediate corollary of this is that so now we chopped up our manifolds into chunks that's growing linearly in size. And now if we know that each chunk, because now they have a diameter bound, if the diameter bound also implies a volume bound, then each chunk also has bounded volume. So that's the assumption we need to make, that the boundary has a weakly bounded geometry. And now, then with this assumption, you can prove that the boundary has, or each end of the boundary has a linear volume growth. So that's one way you can think about this, how the Urysohn widths can be very useful. So any question before we move on?
Yujie, can you please say again which map are you using on the previous slide to estimate the Urysohn width?
You mean to like a graph?
Yeah, you have the boundary on the
Yeah,
left and the
so
right, and then okay,
so
so what is the map?
for
I'm a
example,
little
you know
confused.
that,
Sorry.
yeah, you know this whole chunk is bounded by, has a bounded diameter, so you can just
Hmm.
map it to a point, right?
Okay,
And now this, you can map this just to a small edge that's
okay,
connected to this point. And then, so I'm not drawing the things before, but then you can do the same thing that's connected to a point that has bounded diameter. And here we know that there's two edges, right? And each edge is connected to a chunk that has bounded diameter. So it goes like this. Is this more or less clear?
yeah, thank you.
So yeah, so we're really, this is probably not definitely not the sharpest bound you can have. So you're proving that this whole chunk has a bounded diameter, and that's mapped to a single point. So and this neighborhood of the theta bubble that you're using that comes from the end is mapped to a small edge here. Okay, so now knowing that the boundary has linear growth and our manifold only has non-negative scalar curvature, so it's important to know that we cannot prove the same thing for M, because we can, for example, just take a spherical gap and a spherical cap and then attach an almost Euclidean end to it. Then it has non-negative scalar curvature and mean convex boundary, but you don't have a linear growth for this whole manifold M. So the linear growth really just is for the boundary. It's not for the whole manifold. And of course, the problem is that we cannot use theta bubble because the boundary just lies here. We cannot use theta bubble to try to approximate this end this which has very large growth. Now let's look at applications to this theorem. And one important application is that knowing that a simply connected PSC3 manifold has uniform Urysohn width bound can actually prove that a spherical 4 or 5 manifold has no PSC. And also the localization property of mu bubble allows you to prove that you can connect some with any manifold. So it doesn't have to be closed. It can also be non-compact. So that's a very interesting extension of general conjecture you can prove using mu bubble. And in another direction, you can also try to leverage the linear growth you obtained using mu bubble for PSC manifolds, and try to use this to combine with the second variation to prove rigidity of stable minimal hypersurfaces. So we've mentioned that if we look at the compact case, we have these classification or like these non-existence results. And in the complete non-compact case, so if you look at the non-compact minimal surface inside an ambient manifold that may or may not be compact, then we only know that in dimension 2 that if you have non-negative scalar curvature, you have to be conformal to a plane or a cylinder. And in the second case, you have to be totally geodesic. And we don't know this for higher dimension, and it's also not the exact same analogy in higher dimension. So for example, if you can embed a totally geodesic R3 into R4 so that the sectional curvature is strictly positive everywhere, but the curvature also decays in the sense that you can find a stability inequality on this minimal hypersurface. So even if you have a positive sectional curvature, you don't get non-existence in this case, simply because you cannot just plug in phi equal to 1 here now. And another example is that you can find examples where if you have a Ricci, you can find you can find a manifold where Ricci is uniformly bounded in a small neighborhood, but then you can also map a non-compact stable minimal hypersurface into that region that wraps around so many times so that it's still stable. So what I'm saying is that if you have Ricci strictly positive using the method of second variation, so just by looking at this image locally, without looking at the whole thing, maybe without looking at the global picture, you cannot say that there cannot be stable minimal hypersurfaces. So by looking at these two examples, we need to look at maybe other curvature terms. And this is where the intermediate curvature comes up. So in this case, I'm not talking about the intermediate Ricci curvature that lies between Ricci and scalar, but I'm talking about the one that lies between sectional and Ricci. So this means that if you take any 3 pair of orthonormal vectors, then so if you add up any of these 2 planes that has one direction in common, then the curvature has to be non-negative. And it doesn't really matter what exactly this means, but it gave us a very nice Liouville theorem, which we will talk about later in the proof of the rigidity problem for a minimal surface. So we will be looking at this curvature condition later. And so using this condition, Chodo, Lee, and Stryker proved that if you have non-negative Ricci and PSC, so the first condition gave you control on ends, so on the number of ends, and the second condition gives you linear growth for each end. So combining these two, then you can say that any stable minimal hypersurface in there has to be totally geodesic. So in particular, you can take covering spaces of S2 times S2, S1 times S3, and S2 times T2. Then you can prove that there's no complete two-sided stable minimal hypersurface in there. And for the free boundary case, we want to look at manifolds with boundary and stable free boundary minimal hypersurfaces. And they are just minimal hypersurface inside a manifold with boundary. So they have mean curvature equal to 0. And they also meet with the boundary orthogonally. So aside from the geodesic disk on the equator, we also have this classical example of the critical catenoid that also intersect the ball with angle 90 degree. So we want to look at these minimal hypersurface inside a manifold with boundary. And Giada proved that if you have non-negative scalar curvature and positive non-negative mean curvature, and if one of them has a strict sign, and also the boundary doesn't have any minimal components, then any stable free boundary minimal surface has to be a compact disk. So this is if you're a surface inside a 3 manifold, then you can give a bound of the diameter of this disk by the constant that only relates to the uniform bound you have in the ambient manifold. And we will prove or talk about ideas of the proof for the free boundary case for the equivalent result. Now again, we have this Ricci 2 non-negative condition that gave you the control on ends. But now either we have strictly positive scalar curvature, or we have strictly positive mean curvature. So one of these two has to have a uniform lower bound, uniform positive lower bound. Then this tells us that any complete two-sided stable free boundary minimal hypersurface has to be totally geodesic. So any question about the statement or so far? So now let me try to tell you the idea of the proof. So we go back to the second variation formula, and the goal is to prove that the manifold has linear volume growth inside my ambient manifold. So this is the second variation formula. If I try to plug in a standard cutoff function or bump function here, then I know that the gradient of phi decays like 1 over r squared. So if the volume only grows linearly, then you can show that the left-hand side goes to 0. And the right-hand side we know converges to the things we want to say it has to be equal to 0. So we want to prove the manifold overall has linear volume growth, and there's two things we want to accomplish here. First thing is that we want to control the number of ends of this manifold, and we know that with the assumption of PSC, we know that each end, with the theta bubble case, we don't really have PSC, but we will talk about the detail later. We know that each end has linear volume growth. So if you have control on both these two, then you can prove that M behaves like it has a linear volume growth. But for the number of ends, we know there's two kind of ends. The one is parabolic end, and by definition, you can find a sequence of functions on this end so that the Dirichlet energy goes to 0, but the function itself goes to 1 everywhere. So now if you try to plug in this function into the second variation formula, the right-hand side is what you want, and the left-hand side goes to 0. So these ends are good ends. So we don't have to worry about these. And the second kind of end is the non-parabolic end. And there you can actually have barrier functions. And this is the end we want to try to control the number with. And the Ricci, and that's where the Ricci 2 condition comes from. So essentially we want to show that there's only one non-parabolic end. And that's the only bad one we have. And we know that it has linear volume growth. So then we have n has to have linear volume growth. So that's the idea of the proof. And now let's look at the condition of the Ricci 2 and also 2 convexity. So they will give us this nice property of the minimal surface M is that it has this Liouville theorem, which says that any harmonic functions on M with finite energy has to be constant. So this essentially comes from the second variation, but I think I'm a little bit out of time, so let me not write this down. So either you will have with this condition, you will have either M has finite volume, or it has to have this Liouville theorem property. And the finite volume case is also the case we don't have to worry about. So we just look at the case where the Liouville theorem is true. And now the nice property about the Liouville theorem is that M can has at most one non-parabolic end. So the proof or the idea is that if you have two non-parabolic ends, then you have two barrier functions on these two different ends. So you have two barrier functions, or at least two barrier functions at each end, or like barrier function at each end. So if you have two ends, you can try to interpolate a function between these two barrier functions that will give you a non-constant harmonic functions with finite energy. So the barrier function also has finite energy here. So they will give you a non-constant harmonic or non-constant harmonic function with finite energy. And that will be a contradiction to the Liouville theorem. So we only have one bad end to worry about. And now in this case, with boundary, we also have to be careful about how the boundary, the end of the boundary and the end of the interior manifold interact, because we can only control using Theta-bubbles. So we can also prove that the boundary cannot have any compact components. So the idea is that if you have a compact component, then you can try to double, and if you have one non-parabolic end, and then you can try to double the manifold, then you have two non-parabolic end, then that's again a contradiction to the Liouville theorem. So in the case that M has one non-parabolic end, or N has a non-parabolic end, you can prove that the boundary has no compact component. No compact component. So which means the boundary has to always continuous. And also the last condition is that the boundary has to interact with the non-parabolic ends. So the idea is that you cannot have this image. So you cannot have a cylinder that has what we want, but then you attach an almost Euclidean end to the cylinder, where now you can exhaust the cylinder with Theta-bubbles, but that doesn't really interact with the interior end you have. And again, that's a problem in the case for a manifold with boundary. So what you can prove is actually each end of the boundary, so each component of the boundary has to have an end that lies in the only non-parabolic end M has. So that's another more technical detail. So this image cannot, this image cannot appear. So with these eliminated, then we can try to prove that, and now we can also pass to the universal cover so that M is simply connected. Now, then you can exhaust M using these theta bubbles and prove that it has linear growth, and then that gives you the characterization of that M has to be totally geodesic. So I think that's all I want to talk about today.